good afternoon. We are the second team presenting FIU SAE. We'll be doing chassis, suspension, drivetrain, and ergonomics. I'm Juan Trujillo, this is Michael Suarez, and my other teammate is Frank Delao, and our advisor is Andres Romano. So, piggybacking off what the other team said, Formula SAE is an international competition. We do this once a year where we're able to bring out some of our best engineers and be able to put out a car that is able to represent FIU as a whole and what our mechanical engineering department is all about. So that ties in perfectly into our purpose, which is to obviously design a prototype vehicle, and not only design a prototype vehicle, but also do it in a cost-efficient manner. So like it was previously said, we are designated by the yellow boxes, so we're doing chassis, suspension, ergonomics, and drivetrain. Some of our project goals for the chassis, we had to completely redo the chassis. We've had issues in the past passing some technical inspections with some of the templates, so we wanted to definitely adjust that and with that be able to adhere better to suspension pickup points for the Senior 1 design team. In terms of ergonomics, we wanted to make sure that we got better driver comfort and being able to get out of the vehicle faster, being able to maneuver the vehicle better. In terms of the drivetrain, one of our previous senior teams, they designed a custom differential, which is actually inside of the cockpit right now, and that differential has never been used, so we're actually modifying it so we can mount the suspension pickup points onto those brackets and be able to use that differential. We also went into some testing for that differential to ensure that one, it worked, and two, that it did not wear. So with that in mind, the first topic we'll touch is the drivetrain modifications. So the main point was to bring in the axle more further in towards the rear roll. What that allows us to do is diminish power loss due to an angle in the rear axle, and it also allows us to put the proper amount of tension between the chain and the differential sprocket and the engine sprocket. So for that guy in particular, we're going to be redesigning, we redesigned the mounts so that we're able to incorporate everything in the rear.
So as mentioned before, every 2 years, the chassis has to get redesigned and remanufactured. So due to time constraint and need to adhere to all the components, we just started with re-engineering the chassis that we've had previous years. So from the 2015 to this current competition year that we had. And after Senior Design 1, the choice of chassis was a tubular space frame. The reason of this is because the other type of chassis that are offered are either a hybrid between steel and carbon fiber monocoque or just full carbon fiber monocoque. The reason why we didn't choose any of these is due to the expertise of manufacturing of a carbon fiber monocoque. So in regards to the tubular space frame chassis, after Senior Design 1, as you can see through the yellow circles, there were a couple modifications that we needed to do. One, to adhere to technical inspection, and also to adhere to our actual constraints that we were trying to accomplish with. So one thing I want to point into is the geometry in the back. This geometry allows us to pull in the drivetrain, the differential, so that we don't have to have any tensioner brackets to alleviate the chain clearance that we've had for previous years. And this is the reason why we need to also modify the actual brackets, as Juan mentioned. Another thing that we also integrated is, as you can see, these cross members here. Unfortunately, they didn't pass the actual triangulation that's very crucial in all of the triangulation needs to meet towards one point. And also to reduce the weight, instead of using 3 bars, we came up with the design of using just 1 bar from the main roll hoop all the way to the steering hoop. As Juan mentioned, also something that we were always encountering in competition was passing technical inspection. The reason for this was also clearance within the actual steering hoop. There's a template that we actually brought with us today. This template has to pass within the actual steering hoop all the way through without any intrusions. So in order to accomplish that, we increased the actual steering hoop. And next slide. So in order to validate our actual chassis for competition, we need to pass them through various simulations. We used SolidWorks 2016 to run our initial simulations. The main simulation that they look for is for deflection test. So we need to incorporate a rollover, which has various loads for the actual steering hoop, as well as in respect to the main roll hoop. And a side impact, and a frontal impact. So all of these tests need to pass well with under a 25 millimeter deflection range. All our tests passed. As you can see, the front impact is a 23.45 millimeter deflection, but as you can see, there's an impact attenuator in the front that's going to absorb the majority of this actual impact force. In order to validate our actual SolidWorks simulations, what we did is we furthered our design simulations using a software that's used within the automotive industry that's called HyperMesh software. This allows a more refined mesh to allow more nodal points within all of the tubes to ensure that you get more of an accurate result within your deflection. All of the tests, as I mentioned earlier, the front, side, and rollover impact were done. We have those results, but due to time constraint, I'm just going to go over two unique results that we were able to do. So the first one is the torsional rigidity test. The main purpose of a space tubular frame is to keep all the tubes within tension and compression. The reason for this is the actual rigidity of your frame is what depicts the motion of your actual car when it's experiencing turns or when it's experiencing acceleration or deacceleration. Now, for our torsional rigidity test, we were able to pass as well under the 25 millimeter. And the next test that we were able to do, next slide, was a bump test. We've done frontal impact and understood that it was able to pass. A bump test is basically in case it runs into something, not necessarily the full force of a frontal impact, but just to ensure that even just a quick bump, it would adhere to the deflection test, which it did under 20.81 millimeters. So this is a quick comparison of the three chassis that we've had previous years, 2013, 2014. As you can see, the torsional rigidity was very high. In the design for the prototype 2, which is 2015 to 2016, they decreased the torsional rigidity significantly. As you can see, ours raised just a little bit, but this is well within the range as far as what we need for our application. The high range of torsional rigidity increases the use of adverse handling, so it's very unpredictable what your chassis is going to do when you go into various turns and cornering. As you can see as well, we were able to decrease the weight. 4 pounds doesn't seem like a lot, but any type of weight reduction that you receive in the overall vehicle is great for performance as well. So for the prototype development, we tried to do a lot of things in-house. The reason for this is due to cost and time constraint as well. And due to time constraint of the actual presentation, just going to go quickly over this. The jig and tube bending for the various main row hoops. So you have your front row hoop, your steering, and your main row hoop. All of those were done in-house in order to alleviate costs, as well as the jig manufacturing. We weren't able to manufacture this at the student machine shop due to space and combination with other teams. So my father actually had a space that was able for us to manufacture it there, as well as supply the material for the jig. And for outsourcing, when we first started notching the tubes, we found out that it was alleviating a lot of the inner wall thickness of the actual tubes. So this was going to adhere to the actual overall rigidity of the frame. And as well, when we reached towards these members, as you can see, are very complex in the cuts and joints for those locations. So we outsourced the tubes to get laser notched. We've used a company prior that's called CRD Manufacturing. They're located in California. What they do is they have a laser that is always perpendicular to the tube and is able to cut the profiles exactly to meet to the SolidWorks file that we sent to them. This was the one and only thing that we actually outsourced, and everything else was in-house, the welding as well as all the material used for the welding. The chassis is fully welded, intrusion plate and all. And so to go over ergonomics, for the ergonomics design, everything is basically relative to the packaging, but the main concern that we were focusing on was the rigorous technical inspection that we have to adhere to. So a 95 percentile male, as the template is actually within the actual chassis, this has to be placed within, obviously, your CAD model, and the 4 drivers within the team need to be placed into the vehicle, and a line is placed from the steering hoop all the way to the main row hoop. There has to be 2 inches of clearance from your head to this line that's placed, The reason for this is in case of a rollover, safety is one of the main aspects that they cover over technical inspection. In case of a rollover, your head won't hit the ground and the chassis will actually keep you safe. The cockpit opening template, it's actually over there towards the right. That needs to be able to place within the actual chassis and come up from the range from the steering hoop all the way to the main row hoop. And the egress test, as Juan mentioned, is a test where you need to be able to escape out of your vehicle under 5 seconds in case of anything as far as the engine catching fire or you getting within an accident. You need to be able to get out of the vehicle under 5 seconds. This is also another reason why we installed those side cross members, as I mentioned earlier, to allow you to use that as support to quickly get out of the vehicle. So as I mentioned before, the technical inspection is something that's very scrutinized on all teams. So when establishing the pedal assembly for our system, we took this into account. As you can see, this rail has various slotted holes within the rails. This allows for a pin just to be taken out and maneuver the pedal assembly either forward or backward, adjusting to the various drivers that are going to be placed within the vehicle to pass technical inspection. And in order to adhere to force loads that the driver will be pushing onto the pedals, we did various simulation tests as well. And in order to shave weight, we came up with 3 alternative designs. The third alternative design is the design of choice, one for weight reduction as well as for the factor of safety. I know the factor of safety is relatively high. As I mentioned before, due to time constraint and having to adhere to the various components within the car, we really didn't have time to do various testing. So the 3 factor of safety was relatively high, but adhered to our application, and we just kind of went with it. Thanks. So in regards to the actual throttle pedal, we came up with the design of a 3D printed throttle pedal adjuster. So this is basically a pulley system that's going to be attached to the actual throttle pedal, which will allow for either tightening or untightening to allow for the pedal to reach perfectly to the driver, so we can get full adherence to adhere to great throttle response from any driver that is within the actual vehicle. Another thing to mention is this entire pedal assembly is actually going to be CNC operated through a milling process, and is actually going to be donated to us from one of our team members who actually have access to CNC milling operating machine. And so this is actually a full CAD assembly. The pedal assembly is actually in process now being manufactured. Unfortunately, when cutting out the pedals, there was something that happened within the machine. As we all know, when manufacturing things, we encounter setbacks. So everything as far as the plate and brake pedal is done. We're just waiting for the throttle pedal to be finished so we can integrate everything and also integrate it into the chassis as well.
So about the suspension, we have to correlate with Senior 1 team so we can meet the deadline for competition as well as Senior. We work together with V-Suspension software by setting the track width to 45 inches. We ran an iterative process to make sure that the roll center gets as close as possible to the center of gravity. And so you can see on the left all the geometries of all the uprights and the A-arms, as well as where the suspension pickup points. And this is for the rear suspension because in last year the rear suspension wasn't optimized, so we had to make changes to the rear. So these are our results. We had a rear tire, right and left rear tire camber of negative 1.587 degrees. We increased our roll center from being below ground to actually being 1.45 inches above the ground, as close as possible to the center of gravity. And we increased our roll angle from 0.7 to 1.9 degrees. So another setback from last year was the where the Bellcrank rotated, when the suspension was being affected when the car was in motion. You can tell that the member was bending because the Bellcrank was actually on that member over there that you see on this side right there. That's where the Bellcrank was located, and all the forces were actually bending that member. So we had to look into another design, which is the design you see on the left, which puts the Bellcrank right at the node where right here at the node point between those in the beams, and the shock will be located at the center beam here. So we had to do an analysis. The shock that was outsourced, the only shock was outsourced. I had to remake the shock so that I can see the effects. So I had to input a force of 275 pounds into the wheel's base so that you can completely compress the shock as a critical load. And we got the linear spring constants and the damping coefficients and also gravity included from the outsourced from the where you purchase the shock and the spring. So SolidWorks Motion, we use SolidWorks Motion to find the reaction forces at the where the spring is located, and as well as where the Bellcrank is located, in respectively. As you can see on this side of these results over here is for the shock, and the results on the left are for the Bellcrank location.
Well, we need to wrap it up because you're 15 minutes. You're up. Okay.
So these are the results that it passed. It will not fail during loading. And that's our final suspension assembly.
So really quickly, basically for the cost, we have some of the most expensive components being the suspension and the chassis. So those are totaled under around 10 grand. There's still a couple of expenditures that have to be done, but it's for most of the most crucial components have already been purchased. In terms of global ties, pretty much what the previous team said, we're encouraging global learning by adhering with other universities across the globe and also sharing some of the data between us. We also do some volunteering events, including here at the Engineering Center, Engineers on Wheels, and the Homestead Miami Speedway. Some of the related standards, the most important one that we had to adhere to were the FSAE rulebooks and some of the SAE standards in regards to bolts and so forth. For welding and whatnot, we use some of the ASTM standards. These are again some of our sponsors, and with that, we would like to conclude and open up the floor for any questions.
I just want to make a comment. I know some of the people who are going to be inspecting your vehicle in the next competition, and I would at least look into some sort of secondary retention for your bolts in your system. And by that I mean like some sort of locking mechanism. At least put some thought into it, because due to the vibrational loads you're going to be experiencing, there is a chance that you'll lose a torque on your screw or your bolt, and then your system could literally just fall apart because nothing is holding it in place at that point. That's one thing, which isn't critical, but they'll definitely give you a lot of flack for if you don't even consider it. The other thing is, one thing they don't go over in school is lubrication on bolts, and that's super crucial to maintaining torque in your system when you torque down your bolts. So I would there should be a section of dealing with lubrication in the Mech D2 book that we use at FIU. So I would just take a read of that and see what the purposes of lubrication are, because especially for you guys that build a lot of mechanical systems, when you get to an application with high loads, it definitely makes or breaks your system. And it also allows you to use much smaller fasteners to get the same result, which is nice, because if you're trying to save costs and save weight, that's just a lot of steel that you're removing from your system.
Any other comments?